All right, next we have David Rogers from Stanford University. His field is Earth System Science. He did his practicum at Los Alamos National Laboratory, and his talk is on model-driven verification of enhanced weathering. Let's welcome David.
Hi, everyone. My name is David, or Brian, you can call me whichever. I'm a PhD candidate at Stanford in the DOE School of Sustainability, and my research is on model-driven verification of enhanced weathering for carbon dioxide removal. I'm going to spend some time just orienting you all with the carbon dioxide removal landscape. It's pretty interesting. I find it really exciting. Carbon dioxide removal, or CDR, is defined as any activity that removes CO2 from the atmosphere and durably stores it in geological, terrestrial, or ocean reservoirs or products. So the key thing here is that it removes CO2 from the atmosphere, distinct from carbon capture and sequestration, which is like capturing carbon out of industrial operations. In the near term, we need CDR to remove CO2 that's already in the atmosphere. In the midterm, we need it to supplement progress towards decarbonization. So the priority here really is decarbonization, electrification, renewable energy, but that can only get us so far so quickly. And we can't actually decarbonize everything. So in the long term, we will need CDR to counterbalance emissions from hard to abate sectors. And there are a lot of industry and government initiatives underway right now to scale these technologies. The biggest industry initiative is Frontier. They are an advanced market commitment that was started by Stripe, Alphabet, Shopify, Meta, McKinsey. And it's an advanced market commitment to buy over $1 billion of carbon removal by 2030. There isn't actually like a market demand for carbon dioxide removal right now. They're anticipating it and starting this advanced market commitment so that we can develop the technologies before there actually is demand. There are also some major government initiatives. So the White House just recently started a new unit, the Greenhouse Gas Measurement and Monitoring Interagency Working Group. It's really just about greenhouse gas removal, emissions reductions, quantifying all of that. And the Department of Energy has had a pretty big play in this through their Earth shots. So they have a carbon negative shot where it's just really kickstarting these CDR technologies, trying to get them launched at a cost-effective, in a cost-effective way. The goal is $100 per metric ton. There are other interesting Earth shots like hydrogen, long duration storage, enhanced geothermal, et cetera. To give you just a feel of all the different CDR technologies that are being explored right now, you've probably heard of direct air capture. That's like building a factory to suck CO2 out of the air. Afforestation, you may have heard of. Waste biomass is really interesting. So creating biochar or creating a bio-oil, like a biomass sludge that you inject into the subsurface. A lot of really interesting, cool ideas. I'm focusing specifically on this accelerated chemical weathering of rocks, also known as enhanced weathering. So first, I'll just explain to you exactly what that process is, how it removes CO2. Earth's crust is comprised primarily of silicate minerals. So the bedrock, the soil, those are all silicate minerals. The bedrock weathers and dissolves over geologic timescales. And that's actually how atmospheric CO2 concentrations are regulated over million-year geologic timescales. The bedrock dissolves to create alkalinity, and essentially this alkalinity allows the system to dissolve more CO2. And so more of the CO2 is partitioned from the gaseous phase into the dissolved phase, effectively removing it. Problem is, we are releasing CO2 way faster than the bedrock can dissolve. So we need to enhance this weathering. We can accelerate the weathering by spreading crushed silicate materials across land surfaces, which I will refer to these crushed silicate materials as a feedstock. This is primarily proposed to be done in agricultural settings. Reason being is that it's rapidly scalable if we can integrate it with existing agricultural practices. There is a lot of agricultural land and there's a lot of infrastructure too. So they have equipment to spread fertilizer and lime. We can use that equipment to spread the basalt or the silicate material. There are also a lot of potential agronomic co-benefits. The rocks release nutrients that are useful to the plants, and so that can increase crop yield and also can act as a substitute for liming. A pretty major issue with enhanced weathering right now is the verification. It's an acronym you'll hear a lot in the industry is monitoring, reporting, and verification. Every CDR technology has their own MRV protocol, and it's been really difficult to develop one for enhanced weathering. This is deployed over extremely large scales, so there's a lot of spatial uncertainty, but we also don't actually have sensors to directly measure the carbon dioxide removal. As I mentioned, alkalinity is generated whenever the rock dissolves, but we don't have alkalinity sensors to monitor this. So we have all these imperfect proxies that we're not really sure how well they work. And it's so uncertain right now that honestly, we don't even know if current enhanced weathering deployments are effective and how to verify them and how expensive verification will be. This is really important because verification will be most of the cost, and we want to reach $100 per ton, but right now it's probably $300 to $500 per ton. It's not very clear if we can really reach that goal. My perspective going into this is that there is quite significant unrealized potential for modeling and data science to relieve a lot of this uncertainty, but to also be a very important component of cost-effective MRV. So the main objectives that I have are to apply novel modeling and data science techniques to, one, determine under what conditions enhanced weathering is actually effective. 2, evaluate the accuracy of different MRV approaches. And 3, develop an uncertainty quantification framework to provide consistency and transparency across the industry. Right now, a lot of the CDR startups they're all doing internal verification, and that definitely sets the industry up for some fraud. So I keep saying modeling and data science, so I'll dive into the specific techniques that I'm using and the role that I think that they can play in scaling this technology. The main tool that I use is reactive transport models. These are computational models that couple geochemical reactions with multi-component flow and transport. So we simulate the subsurface environment, fluid flow through the soil and rock, and all the chemistry that happens as that occurs. These were originally developed in the 90s by the Department of Energy to monitor nuclear waste storage. So sites near the Oak Ridge lab and the Hanford site in Washington, lots of nuclear waste disposal. That was the Columbia River. They saw radioactive waste appearing and realized they needed to model the subsurface and figure out where this is going. But since then, these models have been advanced significantly and applied to many different problems. And the scale of these problems ranges from pore scale to watershed scale. A couple examples are simulating subsurface brine injection and CO2 mineralization. Another example is a permeable reactive barrier for remediating hexavalent chromium. There are honestly hundreds of papers that use these models, tons of different applications. So how can we use them to help us with enhanced weathering? On the right here, I have just a schematic of a lot of the subsurface processes that are happening in the soil that affect enhanced weathering. The specifics aren't important, just the fact that it's a very complex biogeochemical network. And not only can we simulate this biogeochemical network with the models, but we can very specifically track different MRV components, and we can test the accuracy of different proxies. So here in this solid phase diagram, this is a soil column that is 2 meters deep, and the dashed line is the initial feedstock amendment, and then you can just see over the first year that feedstock dissolving, going down in volume fraction. And then we have the aqueous component as well, where we have the dashed line is that low initial aqueous baseline, and then the alkalinity increasing over time. So the key thing here is that we can very specifically track components that are relevant to enhanced weathering. And we can also analyze these using very interesting data science techniques. One of them is distance-based generalized sensitivity analysis. So these models have a lot of uncertain parameters. There are probably well over 100 parameters that go into a single simulation. We don't know the values of most of them. A lot of enhanced weathering models, they guess at these parameters. They're probably wrong, which is not good because these models have really been used to support investment and growth of enhanced weathering. What we can do is for all the uncertain parameters, we can apply really wide parameter ranges to them, sample the parameter ranges, and then rank the parameters in terms of how important they are for a specific outcome of interest. So here I have fraction of feedstock dissolved over 20 years. Each line is a different model simulation. And on the y-axis is fractional change. So 0 is no feedstock dissolving. Minus 0.6 is 60% of the feedstock dissolving. And you can see if we actually account for the uncertainty in all these different parameters, a lot of the models don't have any of the feedstock dissolving, which is not good. This means that no enhanced weathering or carbon dioxide removal is happening. And these parameter ranges are representative of the Mississippi River Basin. This is where a lot of enhanced weathering deployments are right now. And yeah, I'm honestly pretty skeptical of this technology, if I'm being honest. And again, we can rank these uncertain parameters in order of their significance and their effect on the outcome of interest. So here we see that the flow rate is actually what is controlling how much feedstock is dissolving. This suggests that the weathering in this kind of climate is transport limited. So just to briefly go over what that means, whenever the rocks dissolve, they release solutes into the surrounding pore water, and the solutes accumulate and the pore water becomes saturated with respect to that dissolving mineral. So the more saturated it is, the slower the mineral dissolves. What you need is flow to continuously flush and dilute that pore water so that the mineral can keep dissolving. And you can see that that's the main control on these simulations representative of the Mississippi River Basin. Upcoming experiments will be looking at the climates of, for example, tropical areas in Brazil. And maybe they aren't transport limited, but pH limited. There are many different possibilities. So to end, just going over what I think the most significant roles of models in data science will be in advancing this technology. First is addressing scientific uncertainties. Like I said in the previous slide, what is limiting enhanced weathering across systems? But also to provide a rigorous and transparent framework for uncertainty quantification and verification. As I mentioned before, we can simulate these different measurement proxies and see how accurate they are. And we can pair that with the geostatistical frameworks to figure out, okay, this proxy has so much uncertainty. So how densely do we need to sample to account for that uncertainty? So that's kind of the other main component of this work is to develop that geostatistical framework that the startups can use to provide rigor and transparency. And with that, I will take questions. Thank you so much.